Hello Physical Science, this is Mr. B, and we're going to finish up Section 2 today, and the focus of Section 2 is going to be something that is known as thermodynamics. So, again, that's probably a new word for you, but we're going to kind of break it down to help it make sense, and there's going to actually be 3 laws that we're going to go over that relates to this term that is known as thermodynamics. So, to start, we're just going to get a definition, and the study of conversions between thermal energy and other forms of energy is called thermodynamics. So thermo has to deal with the thermal heat right there, and then we've kind of used this reference before, a static and a dynamic character. A dynamic character is always changing, and so it's talking about how different energies, energy conversions, again, that's changing from one form to the other between thermal and all of our other forms. So we would definitely write this down, that thermodynamics is just studying how thermal energy is converted into other forms of energy. And there was a guy by the name of James Prescott Joule. You've probably noticed that. That's where the term Joule comes from. He measured energy changes within a system. He included a falling weight that turned a paddle wheel in a container of water. And by doing all of this, and by kind of just keeping all of this isolated, keeping it kind of a closed system, Joule found out that the work that was done by the falling weight almost exactly equaled the thermal energy gained by the water. So when he dropped the weight to cause it to push the paddle wheel, again, he noticed that the same energy or the amount of work that was done by the falling weight, so the transfer of energy there, equaled all the thermal energy gained by the water. And so that's going to lead us to the first law of thermodynamics, saying that energy is always conserved. So that is our first law. I definitely write that down as well. I'll probably ask you what the different laws are. The first law is just that energy is conserved. Energy will always be conserved. And we've kind of talked about this before when we said, again, energy cannot be created or destroyed. We've talked about that before. Again, it is converted into different forms. And added energy increases the thermal energy of system or does work on the system. In either case, though, energy is going to be conserved. So no matter what you do, even when you add energy, in one way or the other, the energy is going to be conserved. It's never created. It's never destroyed. And so an example they give here is that pushing on the pump does work on the system. Again, that's being going into the tire with the pump right here. So some of the work is converted into thermal energy, which heats the air in the pump and the tire. So thermal energy, again, it's going to be a lot with friction again and heat and things like that. So some of the work is converted into thermal energy, which heats the air in the pump and the tire. So again, it's all conserved. None of the energy is actually lost or destroyed at any point in time. So that's our first law, is that energy is conserved. Our second law states that thermal energy can flow from colder objects to hotter objects only if work is done on the system. So we talked about earlier on our first section that heat flows spontaneously from hot to cold. That's just how it works. But you can make it go from cold to hot, but you have to do work on the system in order to make that occur. It's not just going to occur naturally. You're going to have to do something to the system in order for it to go from cold to hot. And again, we just said this right here. I just said this, that thermal energy naturally flows spontaneously only from hotter to colder objects. So an example of something that kind of goes against that is our refrigerator. So a refrigerator must do work to transfer thermal energy from the cold food compartment to the warm room air. The thermal energy is released by coils at the bottom or the back of the refrigerator. So your refrigerator, again, in order to stay cold, it's going to kind of have to release some of its excess energy out out into the warmer surrounding room. So that refrigerator is an example of something that goes from cold to hot. So a heat engine is any device that converts heat into work. So the efficiency of a heat engine is always less than 100%. And then thermal energy that is not converted into work is what's called waste heat. So that's kind of a good, I don't know, I think it's an easy term to remember, because waste heat is just heat that is not used. It doesn't get converted to work. It kind of just gets lost to the surrounding environment. Again, it's not destroyed. It's not created or anything like that. It just goes to the surrounding environment. So a heat engine is any device that can convert excess thermal energy and heat into work. Again, the thermal energy that it does not use to work is known as waste heat. And spontaneous changes, so this term is kind of our, we're going to look at it, I'm going to make you watch a video about something that explains this a little bit more in class. Spontaneous changes will always make a system less orderly and less work is done on the system. So what that means is naturally things are going to tend to want to get more chaotic or more disorderly. When you add more heat to something, again, particles move faster then, so we know that that's like a gas is going to be something that's more disorderly than a solid. So that's what thermal energy, again, if you add that to a system, to anything, it's going to make it less orderly. And the example they give is that if you walk long enough, your shoelaces will become untied. I'm sure we've all had that problem in our life. But if you keep walking, the opposite isn't going to happen. Your shoelaces aren't going to tie themselves back up. So that just means that disorder in the universe as a whole is always increasing. So in this example, again, your shoes are tied, it's nice and orderly. As you walk, again, you're probably going to be generating heat, adding thermal energy, just things are going on. So your shoes become untied. You can't just keep walking and expect them to go back. So that's kind of how nature works. Nature is always, things are always getting more disordered unless we are physically adding work to try to fix that problem. So that's how it relates to the second law. Again, there's a word that's known as entropy that you are going to watch a video about tomorrow in class. It'll kind of try to make this make a little bit more sense, but this is kind of a higher level thing that you'll learn when you take chemistry and physics and things like that. So our last law of thermodynamics states that absolute zero can never actually be reached. So absolute zero, if you remember, is 0 kelvins, and that can never be reached. So the efficiency of heat engines increases with a greater difference between the higher temperature inside, and the cold temperature outside the engine. So a heat engine could be 100% efficient if the cold outside environment were at absolute zero. However, this would violate the third law of thermodynamics. Sorry. And so the third law of thermodynamics, again, absolute zero can never be reached here on Earth. Again, it just cannot happen. We cannot get that orderly. We cannot make things stop moving like that much. So there's a physicist over there in the picture using rubidium laser to cool atoms to using a laser to cool rubidium atoms to 3 billionths of a Kelvin above absolute zero. So slowing down the atoms as much as possible. Again, cannot reach it to absolute zero, because again, that would violate the third law. So you're going to look more at these laws of thermodynamics in class, but that's it for this video, so let me know if you have any questions.